Hello everybody, welcome back to another video. Today we're going to be solving a really cool problem, so let's get right into it. The problem for today is e to the ix. So I'm sure many of you are familiar with the answer to what this is equal to, but today we're going to be proving it. So let's get right into it. Now, as a little precursor before I jump right into e to the ix, I think it's important to know sine x and cosine x. So I'm going to talk a little bit about this. Now, if you've taken Calculus 2, you're familiar with something called the Taylor series. And if you do know what this is, then I'm just going to be briefly covering it and it can be a review. But yeah, so let me draw the graph of sine x very briefly. Yeah, that's approximately sine x. Don't worry about the sharp corners and all that. But essentially, the Taylor series is basically a way of representing sine of x, this transcendental function, using an infinite number of polynomial terms. So if I take a blue point, I'm going to put the blue point right here. All the Taylor series is saying is, hey, I'm gonna create a polynomial that has an infinite number of terms that perfectly matches this entire sine x. But what happens if I take I take n terms of that polynomial instead of an infinite number? So if I take an n amount of terms, what that polynomial will do is try its best to wrap around that focus point of sine x. So if I do this for some n amount of times, it might look like this. Then if I go a little more, it might wrap around like this. It might wrap around like that and then go that way. So it looks like a polynomial still. Now if I do it even more, it might look like this and then go shoot up to infinity and go negative infinity like that. So as I take that nth degree more and more and I increase it, then it'll eventually approach sine of x as I carry out to infinity because it keeps wrapping around that focus point. So with this new knowledge, we're going to give this the representation of sine of x using the Taylor series. Now, I don't want to talk too much about the Taylor series, but I can do a separate video on that. But I will be writing the formula. So for those who don't know about it, I can write it here. F of x, if I have any function f of x, we can say the Taylor series is equal to the summation from n equals 0 to infinity of the nth derivative of the function evaluated at a. A is equal to the focus point on that graph. If I did that, that blue point which I wrap around, the x-coordinate of that is a, just to be clear. So now that's on the numerator. On the denominator, we have n factorial, which is what's incrementing in our summation. All of this is multiplied by x minus a to the n, and a is our focus point. And remember, if you're thinking y is an x here, we're saying f of x is equal to this. So this entire summation should still be a function of x. So I'm not going to be proving this Taylor series, and there are some pretty beautiful proofs there, but for the purposes of this video, I'm just going to be putting this on the side. If you want me to do a video on that, let me know. So using this formula, feel free to take your time to do all that, but the answer for sine of x, the Taylor series expansion, is simply x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus dot dot dot. So you can do this. It's pretty simple to do it using the formula because, oh, by the way, when I have n equals 0 and this is the nth derivative, there's no such thing as like the 0th derivative. What that indicates is just don't take the derivative and evaluate the function at that point. So the first term, for example, I'll just do a few so you guys understand. The first term would just be at the sine of x evaluated at our focus point, and I should specify our focus point for this example is 0. So sine of 0 is 0, meaning the first term goes away. Then we take the first derivative of sine of x, which is cosine of x. We get cosine of 0 over 1 factorial, because n increments, times x minus 0 to the 1. Cosine of 0 becomes 1. 1 factorial is 1. We get 1 times x minus 0 to the 1, and that's how we get our first term right there. Now, if you continue this out, this is what you'll get for sine of x, and it's pretty cool. Now, we can do the exact same thing for cosine of x. For cosine of x, what do we get? We get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus dot dot dot. So you can see right here the pattern is we have even powers going like this and they're incrementing by 2. And we have odd powers here, which is pretty neat on how these work together. So yeah, you can see right here, you can simplify the factorial, but there's no need right now, but we'll talk about that later. So with this new knowledge on how we can represent sine of x and cosine of x using an infinite number of polynomials with the Taylor series, we can now move on to our problem for today, e to the ix. And by the way, for those who are a little technical, this is technically a Maclaurin series because the Maclaurin series uses a as 0. So if your focus point is at 0, specifically at 0, and it's a Taylor series, it becomes a Maclaurin series. So these are the Maclaurin series for sine of x and cosine of x. But back to e to the ix. Now, a really, really cool property of e to the x, if you ignore the I for a second, is that you can represent it using the Taylor series, but it's very, very neat. Because e to the x, using our formula, is just 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus dot, dot, dot. So it continues on and on and on. It's very neat because it's incrementing by 1 every single time, and the denominator also increments by 1. So very cool. So I'll put this on our left side as well. Now we can just plug in certain values, and we'll see how it all unfolds. Now, all I'm going to do to prove what e to the ix is equal to is just plug in ix for x in e to the x. So what do I mean by that? In this Taylor expansion or Maclaurin expansion for e to the x, I'm just going to plug in ix for every x I see because that's valid. Because I can just say that x is equal to some function of I or has some I involved. But let's do that. We have e to the ix equals, what is 1? Does 1 have anything involved with x? No. We have 1 plus x. Remember, for every x, we substitute an ix. So we'll have ix. And I'll switch all this to white, actually. Let's do white. Yeah. So we have e to the ix is equal to 1 plus ix plus, now what is this? What is x squared if x is ix? So this becomes ix squared, right? So I'm going to write it like this. Ix squared over 2 factorial plus, and then we get x cubed over 3 factorial. We have ix cubed over 3 factorial. Then we can continue the process. We have plus ix to the 4th over 4 factorial, and I'm going to go one more, plus ix to the 5th over 5 factorial. Now, let's just simplify. This means that e to the ix is equal to 1 plus ix. Can't simplify that. Now, what is ix squared? All that squared. Now, I squared is just -1, and x squared is x squared. So this becomes negative x squared over 2 factorial. And then what's I cubed? I cubed is just I squared times I, which is just -I. So then this becomes minus I x cubed over 3 factorial. What's I to the 4th? I to the 4th is equal to I squared, all squared, and I squared is -1, and that squared is just 1. So this becomes plus x to the 4th over 4 factorial. And then I'm going to do the last one. I to the 5th is just I to the 4th times I to the 4th was 1, and the 1 times I is just I. So plus I times x to the 5th over 5 factorial plus dot, dot, dot. So now let's observe the pattern here. What are we noticing? E to the ix. Let's look at our I terms. So we have every I term is every other term, just like this. And to continue like this, we'll have a real term, and then we have an imaginary term, like this. So this is our pattern of imaginary terms. And for real terms, we have like this, real, 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 so on, dot, dot, dot. And I'll put a dot, dot, dot there as well. Dot, dot, dot. So what do we begin to notice? We have an I, and then it becomes negative, then -I, and then 1, and then it repeats. So this is a repeating pattern. There's nothing that we have to worry about here. What happens if we begin to group all of our real terms together and all of our imaginary terms together? Let's see. E to the ix is equal to, let's put all of our real terms together. We have 1, real, minus x squared over 2 factorial, real, plus x to the 4th over 4 factorial. This would be real as well. So we can add a plus dot, 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 just like that. I'm going to put this in parentheses to indicate these are all of the real terms. Now, what happens if I group all of my imaginary terms? Now I have plus, I'll do blue, plus ix, imaginary, minus I times x cubed over 3 factorial, imaginary, plus I times x to the 5th over 5 factorial, plus dot, 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 just like that. So this is very simple. We just use the e to the x, we plug in ix for ix, then we just simplified a little bit, and we grouped all of our terms. And now we're here. Now I'm going to clean this up a little bit, just a tad bit. This is going to be the same. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial plus dot dot dot, parentheses. I'm going to factor out an I because we grouped all of our imaginary terms like this. So it's valid for me to do plus I times x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus dot dot dot, just like that. Because all of these terms are imaginary, this is valid because this distributes properly and there's nothing to worry about. So what do we notice? What was the point of doing all of this, of grouping all these terms and plugging in ix and doing all that? Well, if we go back to the precursor and what I stated in the very beginning, I'm going to move all of this down. What did we say that sine of x is equal to? We said sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. That's exactly the same as what we just saw here, this imaginary term. So that means that if these two are equivalent exactly, this is just an I factored out, we can just replace this entire part right here for sine of x. And what do we notice on the left here? We see that this is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial plus dot dot dot. This is exactly the same as what we came for our Taylor expansion for cosine of x. So that means we can plug it in right there. Ladies and gentlemen, that means e to the ix is equal to, what is this equal to? This is right here. Cosine x plus I times, and what was this equal to? This is just sine of x plus I times sine of x. So this is, if you didn't know already, this is the name for Euler's formula, one of his most famous formulas, and very, very elegant. Just like this. It's pretty remarkable and how cool of a formula this is. E to the ix equals cosine of x plus I sine x. This has a lot of usage in like a lot of imaginary different computations and imaginary calculus. Cauchy, he used this a ton. There's so many different applications of this formula, and it's truly remarkable to see what it means. And this is the proof because it's pretty elegant. All it involves is just the Taylor expansion, plugging in I, simplifying, and then noticing how sine of x and cosine of x fit pretty nicely. So this has a lot, it's pretty cool how it all simplifies down like that. Now, really quickly, to discuss the meaning of this statement, we can quickly imagine a plane. So let me draw this one out. Let me draw this. And imagine this is real, and imagine this is imaginary. Imagine, see what I did there? But yeah, imagine that this is imaginary. So all this formula is saying is that if you define a point, any point, let's say that I define this point right here. By the way, in the imaginary plane, we don't describe points by a comma b. I don't say that this is 3 comma 2i. I don't do that. That's not how we do it. In the imaginary plane, we write this point as a sum of these two components. So this point would be 3 plus 2i, just like that. So likewise, if I have a point just like that, oops, let me remove all this. If I define a point right here, and this point is equal to the cosine of x, and this point right here is I sine of x, we would write this as plus I sine of x. We don't write this as comma. So this is the sum. That's what that point is. We're saying that this point is equal to e to the ix. And it's truly remarkable from that sense because we can just describe this entire point and its position and everything about it using simply e to the power of I times x, whatever that input is. And that's pretty cool. So if you are familiar with the unit circle, you might know that if I do this, traditionally, if this were real, not imaginary, this point, or any point on the circle, is defined as cosine of theta, comma sine of theta, meaning that this distance is sine of theta, and this distance right here is cosine of theta, given this theta. So likewise, when we're defining a point on the complex plane, just like this, if I have cosine of x plus I sine of x, any point on the circle can be described by e to the ix, just like that. So it has a lot of physical meaning in that sense too. But once again, very elegant proof. Not mine. It's available on Wikipedia, but very cool. And I hope you guys enjoyed this kind of content. Let me know different future video ideas. If you have any questions or if I made any mistake, let me know. Thank you guys. See ya.